Alrighty, so let's take a look at this warm-up. It says to find the average rate of change of the function over the interval from 1 to 5. When we're finding average rate of change, what are we finding? Yeah, we're just finding rise over run. We're finding slope. Algebra slope is another way we could talk about that. So we're just finding slope. Let me get a hot pink. Okay, and so if we're going to do that, if we're looking at the y values from 5 to 1, looks like that first y value is 400 minus 144. Divide that by 5 minus 1. What's 400 minus 144? 2 what? 256. And we're going to divide it by 4, which would give me 64. All right, so that's our average rate of change, which, again, you've talked about average rate of change since Algebra 1, right? Just looking at a graph. I thought this was a good quote. There you go. It always seems impossible until it's done. All right, so our learning target to start with today is talking about average rate of change versus instantaneous rate of change. And we have a little investigation here that I really like. It's one of my favorite ones. And it says, can a human break the sound barrier? So on October 14th, 2012, Australian skydiver Felix Baumgartner. What do you think? Close. All right. Broke a world record for a high altitude dive when he ascended 127,000 some odd feet in a helium balloon and then went into a free fall lasting more than 4 minutes. That'd be a big fat no for me. Okay, there'd be a full on.
There was a hole in his glove.
Really?
Yeah, and his whole arm swelled up.
Stop it.
Low pressure, because I think he got past the Kármán line, which is the point where we mark where space starts.
Okay.
Either way, he was stupid high altitude and his glove leaked.
Oh, yikes. Okay.
Because he's in a spacesuit.
Oh, Lord. Okay.
Yes.
Yeah.
And what?
He was sponsored by Red Bull.
That makes sense.
Did they get it on, was TikTok around in 2012?
No, but there's a video of it.
There's a video of
There's
it.
a video of it.
Okay, all
Red
right.
Bull's been doing crazy stuff and posting it on
For a long time, huh?
long before TikTok.
Got it. Okay. All right. Good to know. See, I always know where to go for all my pieces. All right. So here's what I want you to do. I want you to take a few minutes and work through this investigation. And it's on a couple of pages, right there with your partners and stuff. So he's in free fall for 4 minutes and 20 seconds, which they equate to 260 seconds, before he deploys his parachute at an elevation of 8,420 feet above sea level. So he wants to know the vertical distance of the free fall as in his average velocity during the free fall. So take a second and work through that. And then take a look at those next few things that they ask us about. Okay, so it goes on several different things to look at. All right, take a minute with your partner and let's talk about those things and see if we can come up with some good ideas. Finally used a whole tablet. Had those a long time. Y'all check out my cute little topper from the Target dollar bins. My husband let me go to Target and touch all the things that all bins. The one on my water bottle's pumpkin, it didn't have an eyeball on it. ready for pumpkin season. That's good. I wasn't thinking to look that tall. They let you come back.
They did. I'm back. I didn't think I would ever leave. So happy to be here.
We're glad you're here.
Okay, at least you got like 3 different options. Yeah. I got like 50. No, you didn't for me.
I was gonna be there long.
Oh, you did? Oh, careful.
None of them sound like really good feelings. They're all like,
Oh, yeah. Y'all quick. All right, let's take just a couple more minutes. We'll wrap up and we'll kind of walk through this. It's really good information.
We're doing, all of the, all of the questions.
and then I sleep, and then I radio, and then they die from radiation. Turn the lights right, forget about it, they die from radiation. No, not the one I work. You've been with her? I've had one too. Yeah, I think it was the button. The big green button, turn it on, it's a big red button. Okay, I have that. My bottom one's not that bad. It's the top one that's really bad. You know what sucks? So we're sorry about having so twins thing coming back. I can only do it one way.
That is unfortunate.
It is.
Yeah.
I hate it.
All right, guys, so let's talk about this a little bit. So it asked me his vertical distance of his free fall. How would I find that? Yeah, we'd subtract where he started with this point right here, which was at 84.20. So 127, 850 minus 84.20. And what do we get?
119.430.
Yeah, 430. Because this is real life, let's put some units on it. Feet of free fall. Okay, so just being good peeps right there. All right. And so then it asked me to find his average velocity. What would we do to do that? What is velocity, by the way? It's his rate of change, right? It's his rate of change, it's distance over time, right? And so his total distance,
I literally said speed and direction. Like, actually, positively, I promise you I said speed and direction.
You did. I believe you.
I'll believe the Madam President.
you believe, Madam President, over our amount of time, which was 260 seconds. Hey, question, okay? I'm going to make that distance negative. Why would I do that?
You going down?
Because my direction is I'm going down, right? So that's why we needed to think about it being negative, and we get negative 459.346. What are my units of measure? Feet per second. It is a rate of change. And we said just a few minutes ago that velocity is a speed with direction. How many of y'all got that in that physical world concepts of physics when you were freshmen?
don't talk
Okay, we're not talking about it?
No.
We don't talk about it? Okay.
We,
So they didn't like it. They're going with a no.
I was fine, I had it second semester.
yeah, she doesn't know what it was like. The first semester, that
You didn't take it? Okay.
like going through Dante's Inferno. It was
That's the
not
only
good.
reason
Okay.
I think I did good, because I got a 50 on the first test, and so she just never marked anything wrong on mine ever.
Oh, I had.
Stop it.
You're the.
Not actually, but like she would definitely ask me things that she
I've been
didn't
wanting-
want.
crazy.
Okay.
Also, yesterday we were on the video.
On that first
it said
test?
that, like, if we do,
I still only
like,
got like an
if we find, what was it, the slope.
I
Yeah,
feel like
the
I'll
people in the
like
class,
that
that was the
So
only
we
good
just
thing.
do, like, y2 minus y1 over that.
The class beats I had.
On a free, I want you to simplify because if you go into college and you don't, your professors are going to eat you alive. But on the AP exam and a free response, we do not have to. Once you substitute in to save yourself time, you don't have to. But sometimes you need the value that comes from that. So, yeah, we'll talk about that as we get closer.
Don't listen to him.
When it's smart, no, you can listen to it, but when it's smart to just be like, all right, I'm going to let this sit because I need to move on to this part of the question. Yeah. All right, so let's take a look at this one. So now they give me a function, all right, and they graph it for me. So it says that t seconds after stepping off the balloon can be approximated his height in feet by that beautiful equation between time 0 and 50, so 50 seconds. And so let's look at the graph of FT. Let's label both axes. So what's this bottom axis going to represent? That's my time axis, and it's measured in seconds. And then what about my y-axis? It's measured in feet. It says elevation in feet. Okay? So the question it asked me is, was he traveling at a constant velocity, and how do we know? Okay, what would a constant velocity look like, you think? Yeah, it would be a straight line, right? We would have constant slope. So if I did the slope between those 2 points, if I did the slope between these 2 points, all of those slopes would be the same, are they? No. Okay, so we say no, lots of different slopes, because that's my average rate of change. And if you wanted to put AROC right there, that'd be good too. Okay, what time does this appear that he's traveling the fastest? In the beginning or the end? The middle? Yeah, at the end. I would agree that he seems to be traveling fastest at the end. Why do we know that? Yeah, one, it's concave down. All right, so we talked about that. It's been a hot minute since we've discussed all of that good stuff from pre-cal. But if we just simply look at the slopes, what's true about the slopes as we go farther? They're steeper. Okay, the slopes are steeper. That's right. We think about gravity, right? Okay, so if we're looking at it mathematically, the slopes are steeper. So now let's look at this next question. It says it wants me to estimate his velocity exactly 30 seconds after leaving the balloon. So it's going to ask me to do his average velocity between 20 and 30 seconds. So how would I go about doing that to get his average velocity? Yeah, we're going to plug it in. We're going to do slopes. So I do f at 30 minus f at 20. So we're going to get some exact values over 30 minus 20. Okay. And so if I plug those into the function, that gives me 113,450 minus a bunch of other stuff, 450. All divided by 10, and so I would get negative 800 feet per second. Okay. So now it asks me, is that faster or slower than the velocity at exactly 30 seconds? What do you think? Okay, I'm going to erase these up here, and let's just kind of look at this picture. We want to know the slope at exactly 30 seconds. So that's like a point of tangency right there. So if I go from 20 to 30, is that slope, right, faster or slower, more or less than what I have at exactly 30 seconds? It's less, right? The slope should be less. Okay, so it's going to be slower between 20 and 30 because the slope is less. Okay. So now they want me to switch it. They want me to do the slope between 30 and 40. Okay, so we're going to follow the same process we just used. F at 40 minus F at 30. So using our equation there. Right, 40 minus 30. That's going to give us some pretty big, nasty numbers too. 102,000 minus 113, 450. Luckily, we'd already done that one. Still divided by 10. That one gives me negative 1,120 feet per second. Okay, so again, just crunching some numbers through that equation, doing some average rates of change. To go from 30 to 40, all right, so 30 to 40, right, is that average speed faster or slower than the exact speed at 30? I didn't draw that one really good, but it's faster. Why would it be faster? The slope is more, slope is greater. Okay. So we're trying to do slope at one point, but to do that, we're having to use a couple of points to make it happen. Now, the next one, they said, well, you know what? Let's get even closer to 30, right? Because we're 10 away, right? Which is a pretty big distance if you're thinking of X values. So on the next slide, they close it in to, all right, let's go 29 to 30 and 30 to 31. Let's get closer to that exact value of 30. And so let's jump in there and look at that one. We do it the exact same way, right? F at 30 minus F at 29. And this time, our time difference is just what? 1 second. So that's nice. So we'd end up with, y'all good if I just write that answer, negative 944 feet per second. So we're just narrowing in, all right, getting closer. We go the opposite direction, F of 31 minus F at 30, still just a distance of 1 on the, or a difference in our time of 1 second would give us negative 976 feet per second. Are those estimates better or worse? Better, yeah. Why would they be better? They're closer to 30. Okay, how could we get even better estimates? Don't say it. We're not ready yet.
The physics.
We could do the physics, but we're not ready. We're doing some math.
The physics is 32 times 30.
So how could we get an even better estimates? Just narrow down the interval. Okay, what if we could make our time distance 0.5 or 0.05 or 0.005, right? The closer we could get to exactly 30, the better off we would be. Okay, now what I want to do here for a second is just kind of rewrite what we did up here in the first part, okay? Because we're interested in 30, right? We're interested in 30. So basically what we did was this. See if you can follow me. We need F of 30 minus 1 minus F at 30. Oh, stop that. Stop it. Over a difference of negative 1. For the second one, we did f of 30 plus 1 minus f at 30 over a difference of positive 1. Where do you think I got those values? What do you think? Well, let me ask you a question. When we do slope, do we have to do the second one then the first one? No, we can flip-flop the points, right? Slope is slope. It's going to work itself out regardless of which value we put in first. So f at 29, I did 30 minus a change of 1, right? F at 30, that gave me 29. F at 30. And then this difference, if I switched it around, it would be negative 1. I have that distance of negative 1. Here, to get 31, I did 30 plus 1, right? Then used my 30. The difference between the two is a positive 1, okay? So now I want you to look at what it asked me to do in this next part, okay? It says, all right, let's pretend that h is this arbitrary distance, okay, from 30. We're looking for a slope that's close to 30, right? But we still need 2 points to do it. So we're going to break it down into some steps. First, let's find f of 30 plus h. First of all, how would I do that? What would I do? How would I find that value? It's going to be an algebraic expression. I just plug it into the function, right? And my function was 127,850 minus 16 times whatever we plug in squared. Okay, so I'm going to plug in a 30 plus h. So we're just going to do some fancy algebra right here. All right, so just a lot of little algebra. Okay, I'm going to keep that 127,850. I'm also going to keep the 16. Now, to square 30 plus h, how many terms will it give me when I square that? It will give me 3. Okay, it'll give me 3. You can write that out, 30 plus h times 30 plus h, or if you kind of remember the shortcut, square the first, so that'd be 900. Multiply the 2 together times 2, so 30 times h times 2 would be 60h, and then square the last. Okay. And then we would distribute, okay, and combine some like terms. All right. So that gives me 127,850. 16 times 900, 0, 0, 4. Is that 144? It's what? Okay, minus, is it 90h? Minus 16h squared. All right. And then we subtract. And we end up with 113,450 minus 90h minus 16h squared. Did I do that algebra right? That was a lot of algebra right there. Check my math, because I did that in my head.
It's 960.
You're right, it's 960. I don't know what I was thinking. Appreciate you.
You added an extra 0 to 144.
It would have 2 zeros, right?
Yeah.
Okay. Is that better? Doing math in my head is dangerous. Okay. Phew. There are days that I wonder.
I just rolled with the big one, the rest of it.
The rest of it looks right.
From the standing.
Gotcha. I appreciate that. Okay. So now it wants me to take f of 30 plus h and subtract f of 30. Well, y'all, we did f of 30 plus h. It's this big nasty expression right here. So I take 113,450 minus 960h minus 16h squared. And then we're going to subtract f at 30. Well, we've done that 100 times up to the top. Okay, that number is 113,450. What's going to happen? Yeah, it cancels out, right? I lose that 13,450, and it leaves me with negative 960h minus 16h squared. Right? Now it says take it one step farther. Okay? And take that expression you just found and divide it by h. Okay? Take that expression you just found. So the expression I just found was negative 960h minus 16h squared. And I want to divide it by h. What's going to happen when I divide each of those terms by an h? Their things are going to reduce out, right? So negative 960h divided by h, the h would go away. I get negative 960 minus the next side, 16h squared divided by h would give me 16h, right? Now, that computation that we just did was not just for fun, okay? There's a reason we did it, okay? We refer to that as the difference quotient, okay? And the reason we call it the difference quotient is we take some x value and we go a distance away, all right? We went some h distance away. Could be 1, could be 10, right? Could be 0.1, right? Then we subtracted the value of the function at that x value, and we divided it by h. And I'm going to show you where that comes from in just a second. That is an average rate of change. Okay, it's an average rate of change, all right? And here's where it came from, all right? I have x and x plus h, all right? When I do the algebra slope, the average rate of change, that bottom part, if I did x plus h minus x, what would it result in? Just a plain old h, okay? So it comes from the average rate of change formula between x plus h and x. Now, we call that the difference quotient. The next part it says is what we have to do to get the velocity at exactly t equals 30. What would we need h to do? Do what? Get closer and closer to 0. All right? What have we done so far that allows us to get super close to 0? A limit. Okay? We'd need to take a limit. We'd need to take the limit as h gets really close to 0 of negative 960 minus 16h. Well, how do we evaluate that limit? We plug in 0 for h. Okay? So I have negative 960 minus 16 times 0, which is just negative 960 feet per second. That is his exact velocity at t equals 30. Okay, so we're looking for our instantaneous rate of change, and when we take the limit, it brings me to the instantaneous rate of change. Right? So then that last question, it says the speed of sound is 1,125.3 feet per second. Did he go supersonic? At t at 30?
At T30
No,
now.
no, he did not. Not at t30. Not at t equal to 30, which is what we were checking. Okay, not at t equal to 30. Okay, so all that nasty algebra you just looked at, that's how we find the instantaneous rate of change. Okay, that's how we find the instantaneous rate of change. Is there a shorter process? Yes, but AP requires you to know the long process along with the shorter process. We will get to the shorter process next week, so there's something to look forward to. Okay?
This is the highest answer multiplied to
I agree. I agree. All right, I agree. But they hold you responsible for all of it, so we got to be sure we hit it. Okay? All right, so average rate of change of a function, we're going to put it in abstract form. Okay, average rate of change, easiest said is the algebra slope. Okay, so if I'm talking about an interval from x to x plus h, we're going to find our average rate of change by taking f of x plus h minus f of x over x plus h minus x, which simplifies to f of x plus h minus f of x over h. That is your difference quotient. You will see that referenced. Okay? Your difference quotient. Okay? Difference quotient is just average rate of change. It is your algebra slope. Okay? Instantaneous rate of change, the only way to do it is to take the limit of the average rate of change. All right? So we will take the limit as h approaches 0, f of x plus h minus f of x all over h. It's the limit as h approaches 0 of the difference quotient. Now let me draw you a picture. Okay. So let's say that this is my picture f of x. Okay. And here is my x value x, and I want to know the instantaneous rate of change at exactly x. In other words, I want to know the slope of the tangent line. At x. Okay? I want to know the slope of the tangent line there at that x value. Okay? To calculate slope, how many points does it take? It takes 2. Okay? There was a good song from the 80s about it takes 2. Okay? So or maybe that was the 90s. Not sure. Anyway, at this point I've slept so much I don't remember when things came out. Oh, is that your tagline? Oh. We need a shirt. Okay? No?
I don't know about that.
Okay. So this says, hey, to get my second point, we're going to go some distance, h, away from x. And we're going to call it x plus h. And so we're going to do the slope between those points. But if I take the limit of it, then I'm going to find the slope at that exact point because I want h to get as small as possible. I want that distance to be as little as possible. All right. Now, there is an alternate definition. Okay. And I can't remember, did I put that on the same page or is it later? When it says an alternate definition. Check your packet for me. I'm not sure that it, no, I didn't. All right. So we're going to do it right here. Okay. This is the main definition for the instantaneous rate of change. Okay. We'll call this definition 1. Okay. But there is an alternate definition, right? And the alternate definition just looks a little bit better. And people are like, well, why would we need 2 definitions? Well, there's actually 3. but these are the ones that they pick the most. And I will show you the third one tomorrow. Okay? Or maybe today. We'll just see what happens. So let's say we've got this exact same thing, all right? But this time we've got some value called a that we're trying to get really close to, all right? So we're trying to find the instantaneous rate of change, right? So we know it needs 2 points, so we're going to choose some arbitrary point kind of away from a, and we're going to call it x, okay? We're going to call it x. And so we have to have 2 points to approximate slope. Right? And so if I was going to do just the rate of change between x and a, we would write that as f of x minus f of a over x minus a. Okay, so just the average rate of change. But if I want it to be instantaneous, I got to have a limit on it. Okay, I got to have a limit. What needs to happen to my x value in order for me to find this slope at exactly A?
X approaches A.
X approaches A. This is definition 2. They refer to it as the alternate definition. Okay, so it's still a difference quotient. It's just prettier. Okay, than one with all those H's and stuff in it. It's the exact same definition. We just redefined the variables. All right, so let me pause for a second. Okay, that's where that big nasty definition came from yesterday that you saw. All right, in the video. Questions? Because I want you to understand where it comes from. Because it's going to help us moving forward. These first 3 lessons are really kind of foundational to what's coming. So, I have pineapple cotton candy. It's very good. Last night I had raspberry cotton candy. It was good. I love my flavors. Okay.
It was definitely you, Juwan.
All right, so let's take a look at this one. All right, this was the one that was in there. Was this the one where he showed you his cat? He talked about his cat, his helicopter? Yeah, yesterday. So the altitude of Kong's helicopter is given by this. It gives us certain values of it. K of t and then E of t. E of t is a function they gave me. K of t is a table of values. All right, and so it just wants us to find average rate of change. Okay, if I'm doing it from the table, all right, which is what K is, what are my units of measure going to be right there? Feet per minute, right? It's always your y variable over your x variable, okay, or your dependent over your independent, all right? So we would do k at 20 minus k at 5. So we're just doing average rate of change over 20 minus 5. So that one should be pretty simple. We can pull it straight from the table, and that we'd have 15,000 minus 3,500 over 15, and we would get 766. Ooh, that was a funny 6.67 feet per minute. Okay, units of measure are going to be really important in these. If they give you units, you want to use them. Okay, so that's from a table. The second one is from an equation. So again, it's not asking me for a limit. It's not asking for instantaneous. It just wants an average rate of change. So this one would be E at 20 minus E at 5 over 20 minus 5. So we'd have to evaluate the function. Probably a calculator question. All right, so we'd be able to do that one a little bit nicer. And it would give us 625 feet per minute. Okay, so just average rate of change for those. So let's just see if we can set up that instantaneous rate of change expression, what it would look like. Okay, so just set it up. Oh, don't you go back? And AP is notorious for writing problems about weird things. That's why there's an artichoke problem next. Okay, like they just write about weird things. We write about potatoes, we write about bananas and monkeys on an abandoned island. Like they just write problems about really strange things. Okay, so look at this one. So if we wanted it to be an instantaneous rate of change, okay, at t equals 7, what's for sure one thing we got to have on it? A limit, okay? Anytime you want an instantaneous rate of change, there's got to be a limit. Let's use the big definition, limit as h approaches 0, okay? We know in that average rate of change formula, the bottom, it always works itself out to be h, which is really nice. Okay, we're talking about Estelle on this one. So at times 7, so we do E of 7 plus H minus E at 7. Okay? That's what we do. Now, we're not going to work it out, but that's how we'd go about the process. Okay? All right, let's take a look at the next one. I think we get the average rate of change. Let's make sure we understand how to get the instantaneous rate of change. All right, so the above equation gives number of artichokes each hour after midnight. Okay, so it wants the average rate of change for artichokes between 6 and 11 in the morning. All right, so let's talk about that. How would I find the average rate of change? A of what? 11 minus A at 6 over 11 minus 6. We're not going to figure it out, but what would your units of measure be? Artichokes per hour. Okay. I told you they're going to write some crazy stuff. Okay. So now let's put it as an instantaneous rate of change for it exactly 9 in the morning. Okay. What do you got to start with if it's exactly 9? We got to start with a limit. Okay. We're going to do as h approaches 0. H is going to be on the bottom. Okay. What time am I concerned with? 9. So I got to go a little bit away from it. 9 plus h. Minus A at the time that I want. Okay. And that's my expression. Right? So I wanted to spend today making sure you understood where that expression comes from. Okay. Question on that. That should help you be able to work through that 2.1 assignment from yesterday, that worksheet. Okay. Help you a little bit with that. What I want to do next is I want you to go ahead and load up the 2.2 lesson. We won't finish it today, but we're just going to start, all right? Because I think in what I'm going to show you, it will help you, and we can get through things quicker tomorrow, right? So let me export this. Hang on just a second. Document. Put it in my Google Drive. All right, are we good? So I'm gonna close this one, open the next one. Sure, here we go. All right, so let's open 2.2. Okay. Gareth, I picked this affirmation for you. Lillian saw the apple fall, but Newton asked why. Okay. All right, let's actually do this warm-up. All right, together. All right. Pulled it from AP Classroom. It says, let f be the function defined by f of x equals e to the 2x. The average rate of change of f over the interval 1 to b is 20, where b is greater than 1. Which of the following is an equation that could be used to find the value of b? Take a second and think about it. Which one would work to find the average rate of change?
Did that homework yesterday, I didn't know how to do this type of question.
Yeah.
So, yeah.
Okay, I'm going to help you.
When
You're ready? Yeah, we're going to be ready. This what I'm about to show you is going to help. Okay. All right, what do you think? We're looking for average rate of change over the interval from 1 to b. Okay, so if I'm doing average rate of change, okay, I would take f of b minus f at 1 over b minus 1. That gives me average rate of change. But they also tell me what it's equal to. What's it equal to? It equals 20. So which one of our options is going to be that? C. C is the correct one. Okay? The reason we talk about instantaneous rate of change is because it's leading us to what we define as differential calculus. All right, differential calculus. We do two types of calculus, differential and integral. All right, forward and backward. That's all we do in here, okay? So differential calculus is calculus involving the derivative. And there's a lot of things that involve the derivative. Okay, a lot of which we talked about last year in pre-cal, but I didn't talk to you about a derivative. Okay, so it's calculus involving the derivative, which is an instantaneous rate of change. I don't know what that letter is I just wrote right there. There we go. Okay, so congratulations, we have entered differential calculus. We start with limits because limits are the building blocks of all things calculus. And now we're going to march ourselves right into derivatives.
That's all. Is that anything to do about being out?
Yes,
Is he okay?
he's okay, but he's just going to be out for a little while.
Okay.
Yeah. Y'all can say hello. I'm recording for him. Hello. Okay. All right, so let's talk for a second about the derivative, okay? That limit of the difference quotient that we just talked about, that limit of the average rate of change, congratulations, that's a derivative. Okay, so the derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. That's what it is, okay? Or if we use that alternate definition, we could say the limit as x approaches a of f of x minus f of a over x minus a. Both of those are a definition of the derivative. Okay, what does that represent? Well, all the things we just did a few minutes ago. All right, it represents the instantaneous rate of change. At a point called x. Okay. Or in that alternate definition, at an x value equal to a. Another way to say that, when we first started looking at Baumgartner, we were looking at his slopes. All right, the slopes of the average rate of change we're talking about an instantaneous rate of change, so it is the slope of the tangent line to the curve at a point. My favorite way to refer to it is the limit of the average rate of change. They would say difference quotient. We'll also say that that's just an average rate of change. Okay, that's what a derivative is, all right? In its most complex sense, all right, which we have to understand that it all comes about as being the limit of that average rate of change, okay? Now, this is where that alternate definition comes in, all right? We're going to do some here in just a second, all right? We already did one, okay? We did that one, the limit as x approaches a of f of x minus f of a over x minus a. But I want to show you a second one, okay? The second one is referred to as the symmetric difference quotient. Right, the symmetric difference quotient. So let me draw us a picture. Let's take that same function that we've been using, all right? And we've got some x value that we're going to call a that we're looking for, all right? So we're looking for the derivative at that point. And it takes how many points again to find an average rate of change? 2. It takes 2. So it says, you know what? Let's do a point up here that we'll call a plus h. And let's do a point back here that we call a minus h. All right, so it's symmetric about the point that I'm looking for, okay? And we want to find the slope between those 2 points, okay? How would I find the slope between those 2 points? F of a plus h minus f at a minus h over a plus h minus a minus h. So I'm just doing slope between those 2 points, okay? My y values and my x values. That numerator, I really can't simplify any, so I'm just going to leave it. So f of a plus h minus f of a minus h. On the bottom, let's distribute that negative and talk about what happens, okay? What's going to happen in that denominator? Yeah, it should simplify down to 2 h's. The a's are going to go away, and so I get f of a plus h minus f of a minus h all over 2h, symmetric difference quotient. Now, that's still just an average rate of change. How do I make it instantaneous? I need a limit on it, okay? Now, let's think about what needs to happen. I've gone this h distance away, all right? What does my limit need to be? H getting smaller. That distance away gets smaller. This is that third definition, okay? I've seen it on about 1 in every 5 tests, okay? So that's why I continue to show it, just for that reason. I don't want you to be surprised. Do what? Yeah. Yep, it's just the midpoint. Yep. Yep, it's just the midpoint. Okay. Now, when we want to figure out a derivative for right now, we're going to use these big nasty limits, right? But let me give you some notation. What notation do they use for the derivative? The most common is what we refer to as prime notation. Y prime or f prime at x, okay? So y prime f prime of x, okay? That's how we'd say that, okay? So that's notation for the derivative, right? Now, you know there were 2 guys involved with the whole thing with calculus, right? Newton wanted to take all the credit, but Leibniz was like, no, me too. Okay, so he has his notation, and this is his notation. dy dx, okay? And we would say that derivative of y with respect to x. Okay, so those were the 2 basic notations for derivative, okay? Newton and then good old Leibniz, right? So after that came lots of variations thereof, all right, as, you know, people got involved. So I just want to show you all the different things you might see. You might also see it written this way. They might say df if it's a function, dx. This is my personal favorite where they can't make up their mind, so they combine the two, kind of. Okay. They do d dx, and then they put an f of x next to it. It's still the same thing. We're taking a derivative. Right? I already showed you f prime of x. And then this is one, I'll be honest, I've never seen this notation in anything that I've personally worked with and all the different calculuses I've taken. I'm not sure where that one shows up, but I like to show it, all right, because you just never know, all right? But it is the derivative with respect to x of y, okay? It all still means take a derivative, okay? That's what it all means. So the different notations. The ones you're going to see the most are this one, and probably this one, okay? So I would think those are the three that you're going to see most often. They're the ones I remember seeing the most when I was studying calculus, okay? And so let's run through one, all right? Actually doing the derivative. It should help you to be able to do the one that was on your homework assignment yesterday, okay? So how do we go about right now, without all the cool shortcuts that are coming, doing this the long way, all right? Or to quote Gareth, the hard way. Probably the unnecessary way, right? Because AP says we have to. All right, so let's take a look. I want to find the derivative with respect to x at x equals 2 if y is equal to 2x squared minus 3. This means that we're going to do that big nasty limit. We're going to do the limit as h approaches 0, f of x plus h minus f of x all divided by h, okay? So notation here is really important, okay? We can't get sloppy with our algebra. We have to be really, really careful. All right, which x value are we approaching? -2. That is our x value in question. So we're going to replace all the x's with -2 and leave everything else the same. Okay, so the limit as h approaches 0, f of -2 plus h minus f at -2 all divided by h. So that's where we start. Okay. So we plug in the x value that we're considering into that equation or into that limit where x is at. Now, we just got to simplify that algebraic mess, for lack of a better word. I almost said a bad word. In the middle, okay? It's just a bunch of mess, right? So we're going to keep the limit as h approaches 0, right? Let's start with the first part. Here is my function, 2x squared minus 3. So I'm going to take 2 times -2 plus h. I'm going to square it, minus 3. Okay, so that's the first part. Minus, and I'm going to use parentheses here so I don't goof up, f at -2, which means I'm just going to plug -2 into the function. So 2 times -2 squared minus 3. The h stays on the bottom. Right? So all of my work is in that numerator. Okay, all of my algebraic mess is in that numerator. All right. Again, I'm going to probably show more steps than some of you might need, right? But here we go. Right. So the limit as h approaches 0. All right. I'm going to keep that 2 for a second. When I square -2 plus h, I get 3 terms. That's the most common mistake I see people make in a hurry. All right, they just put 2 terms down, right? It's 3. So that's going to give me a 4 minus 4h plus h squared, and then minus a 3. Minus, then I'm going to get a number for that last part because there's no variables back there, okay? So -2 squared would be 4 times 2 would be 8 minus 3 would be 5. Okay, all over h. All right, we're getting closer. Right. Let's distribute, let's combine like terms, let's hope some things go away. So I have the limit as h approaches 0, 8 minus 8h, h plus 2h squared minus 3 minus 5 all over h. All right, what do you notice? Yep. all the constants should cancel so that you're left with nothing but terms that have an H in them. Okay? If it doesn't, you did some algebra wrong somewhere along the way. Okay? The constant terms should always go away. All right? So that's going to leave me with the limit as h approaches 0 of negative 8h plus 2h squared all divided by h. And I really wish I could stop right here and just plug in 0. But what happens if I plug in 0 for h? I get 0 over 0. It's indeterminate. So what do I have to do? I got to reduce. Y'all are so smart. So limit as h approaches 0, negative 8 plus 2h. Now can I do substitution? Yes. And when I do substitution, it gives me negative 8 plus 2 times 0, which is just negative 8. Congratulations, you just found your first derivative. Okay. It took a lot to make it happen. All right. A lot of nasty algebra along the way. Okay. So let me pause. What questions do you have before we do the next one? We're going to get one more in before we leave. Yes, sir.
Just to clarify, negative 8 is the slope at negative 2.
It is the instantaneous rate of change. It is the slope of the tangent line at x equals negative 2. That's exactly what it is. Okay, good. All right. Does the next one ask you guys to do the alternate definition, the next example? No, that's when we start the investigation. Okay. All right, so I am going to stop right there because I want to start with the investigation tomorrow because it's really good. It leads us to the next part of this, which is really awesome. So here's what I'd like to do, okay? You had a wrap-up yesterday on your Google Classroom. Go in and do that one, all right? So go into yesterday's lesson on Google Classroom and do that wrap-up, okay? Not adding any extra practice, okay? If you weren't able to make sense of what I gave you yesterday on that 2.1, work through that. There's some copies of it back there. Tomorrow, we will finish this and probably get through, we should be able to get through the last part because it's real easy, 2.3, okay? So we can keep our quiz on Thursday and then we'll start 2.4 on Friday, okay? That's it for your first derivative quiz. All right, so just to kind of give you a heads up of where we are, okay? If we don't make it, we don't make it. It is what it is, and we'll adjust as needed. So again, I apologize for not being able to be here yesterday.
It's okay.
Okay, well, I appreciate the love.
You're here now.
I am here now. Okay, next week I'll be out on Thursday. I have to go to my 4-month surgical follow-up, so I'll be in Nashville most of the day.
4 months already?
Yes, can you believe it?
Probably.
I know, it seems like yesterday. But anxious to go. I still have really weird days, like this shirt is like a lot smaller than what I'm used to purchasing. I bought it this weekend and I thought, oh, that's a cute shirt. And I put it on, I'm like, oh my gosh, it fits. But then I still am like, I don't think I look any different, but I do look different. But it's just, your brain plays really weird tricks on you. So anyway, okay. All right, y'all. All right, so do your wrap up that was on Google Classroom for yesterday. All right, and get that submitted and then we'll pick up. Okay, I'm gonna work to get your progress checks in today. I didn't get those in before I left on Friday. Okay, so I'll try to get those in today. Oh, and then let's talk about your test. Sorry, let's talk about your test. You should give yourself a hand. All right, I was proud of you. If you would like to do some additional test corrections, you are welcome to come in and look at your test and see. Let's try to get those done by next Monday. Okay?
You still have to have it below a 60 to do that.
No. So you can still, regardless if you've got, unless you got everything right when you did your corrections, okay? And so if you want to know if you got everything right, I can tell you. I got them back here.
I got everything right. According to them, I got it.
But I don't give them back until we have finished the second round of corrections.
I found the extension for Chrome.
So,
It just has.
are y'all okay if I just tell you? Jacob, you still got one thing you can correct.
Don't tell me how many, please.
I won't, you've got a couple things you can correct, hopefully. Bryce, you're good. No, Bryce, you still got one thing you can fix. Laura, you're good. Solomon's got something he can fix. Parker, you got something you can fix.
I'm checking Gus, so we'll see if I
Oh, yeah.
Justin, you're good.
That's so tight.
Joab, you got some things you can fix. Himmel, you got some things to fix. Nene, you still got something you can fix. Madeline, you got some things to fix. Garrett, I think you're good. Hold on. Yeah, Garrett, you're good. And then Samuel, you got some things to fix.
It's definitely interesting, but you should, actually, there are funny moments.
But it works.
Yeah, I'm seeing out the range. Just here with the fringe.
I just feel.
Yes.
This is basically just the exact.
Okay, right here.
This is multiply the.
No, that's not what we're looking for. No, they won't give you credit for it.
One of our actual.
Oh, no, then I don't care.
Should I correct my one question?
Question
I have 95 already.
don't.
I need to
I did not. You do not
I
have
need to get a
that.
96.
It's just literally one.
I need to get a 96.
So.
Not to make an argument, but I did
No, I can.
because
Just
I
watch
went away,
hearing
and
band
one of them that I
vlog.
missed was.
You can tell it's like. And I heard auto tune.
I scratched.
There's no auto tune.
So.
Look at it here.
Instrument, band.
Yeah.
Oh.
That's easy.
I love that boy, but he needs to learn to keep time. I can't handle.
Who?
He makes me soft. I love him, but that's Dawson. We love Dawson.
Why did they have two?
Trumpets, you guys need to work on time.
No, it's just Esau.
I'm glad I got.
Yeah, but they're working as a collective.
On the first one, I got. Actually,
It rubs off.
Okay.
When was that?
Still,
Yesterday.
you can still do, you'll get, you get 5 points back for when you get.
How much effort did he?
Maybe I'll do it on Thursday.
Oh, he don't.
Right? I'm like,
So I'm. Oh, that's.
It's worth a shot. I mean, at this point, if there's 4 choices, you got it down to 2.
Yeah.
Right? I mean, it's worth the risk.
How many points do I get for this grade?
I hate her. I love her so much. But
It's worth, I'm telling you, it's worth coming late.
she's just so funny.
That's true, you do.
Do I?
Just remind me. It's all for me.
Just tell me more.
There you go. Nice pen.
How good's your water?
Oh, you don't get
How good's your water?
How
What's your water?
Did you see us up there dying yesterday?
Did you do that with
Carrying that crap?
No, so I was facing this way. Yeah.
Yeah, probably Maddie.
Yeah, so.
You know,
I know, it's great. I love it.
Thank you.
But I am about to fall asleep. I almost fell asleep driving, whatever.
Whatever. How behind are you in personal
He cut out
finance?
the second
I
one.
thought it would take 2 hours.
Instead of that,
I've caught up.
You caught up. See, what I spent all of my yesterday putting a week and a half ahead in my environmental science class.
I
So
Oh, this is
I was
cute.
never behind. Like
I'll go
I
sit
was
down and do my
behind.
personal finance tonight.
They're cute.
I hate it. So.
Now, you gotta ask Danny that question. How far behind
Dude,
is
Danny
Danny?
works on personal finance constantly, and he's still like a week behind. I don't even.
Welcome to my favorite game show. How far behind are you in personal finance? You need to ask Danny that.
Danny lost his iPad.
Oh, yeah, it is.
So he doesn't, he can't
He
do
can
his
do
class.
it. He can do it on his phone.
How did he lose his iPad? I don't know, but
As
he
it
asked
approaches
the
your
library to find it, and they still have it.
Oh.
Oh, that's
Daniel
zero?
McKinney. How did you lose your iPad?
Yeah, that's what I
Did he
thought.
bring it with
With
him to
X
the
outside the limit. Look at it.
So, guess what? It would be to E, which would be, it would be 1, right? If you put it at X. Yeah, but
Yeah, it looks really
Whatever the number is.
Because I thought with X on the outside, because there's an X right here that multiplies the entire thing.
Okay. But that's zero. Sure.
Right? That was my first answer, but I got it wrong.
No,
What was your second?
I'll get it done, I
My
promise.
second answer was, the limit.
Oh my God.
It's on my to-do list for this week.